third day, which is the technology panel. At the first beginning, I'd like to acknowledge the organizing team, Omar Siddiqui from EPRI, and who has been hosting for the last couple of days. And my name is Liang from Stanford University. We also have Nicola Peill-Moelter from VMware as organizing team. We receive a lot of guidance from Mark McGranham of EPRI, VP of Innovation. And we have the technology support from Aurelie Welsham from EPRI. She is running the webcast at this moment. And also Wahila Wilkie from EPRI and help on the logistic perspective. Next slide, please. Aurelie, I'm not able to move my slide.
I just advanced the slide. You should be able to see slide number 2.
I think there's a little bit delay on the slide. I'm still on the slide number 1. Okay, let me go to slide number 2. Okay, there's some housekeeping items. Everyone is auto-muted. So there's 2 ways you can ask questions. And we strongly prefer you type your questions through the chat function below. Also, you can raise your hand. Then Aurelie are going to unmute you so that you can ask questions. We are recording this webcast, so your participation is your consent. And all the recordings and the presentations for these 3 days will be available at both EPRI and the Stanford website in the next a week or 2. So quick recap about Omar mentioned in the last couple of days, the objective for this week's session. So EPRI and presented a very good vision of a shared integrated digital grid. And when we go to the actual implementation, there's a key research question is how we can come up with a standardized data platform. Now, that's the reason why we convene experts from different disciplines and regions, including utility in US, utility in European countries, and technology providers, IT companies, academias, to identify gaps to achieve this vision and how we can have and enable a standardized data platform. So utility has already shared some of their requirements, their ideas, their plans, and we're discussing the technology, how we can bridge the gaps in this session. And the key purpose for this week's webinar is to see how we can come up with a research roadmap and also in the future, a collaborative research effort. So quickly mention who is EPRI, what is Stanford. You know, EPRI is an independent non-for-profit organization and conduct R&D in generation, power delivery, and end user for the public benefits. And EPRI's members represent 90% of generation in this country and also has more than 40 countries international members. And Bits and Watts is a Stanford initiative and focusing on the digital transformation and innovation for the 21st century power grid. And we came together last winter and with a lot of help from the IT company from VMware and have the same workshop goal, which is convene utility, technology provider, academia leaders to develop this roadmap and also to inform a collaborative research effort, as I mentioned at the last slide. So today is the last day for this week, but that's not the end for this conversation. We're going to start the weekly summer webinar series from July 1st. So the first webinar will be a recap and the lessons learned from this week. Then we will have several startup company in Bay Area across country discuss, from innovation perspective, what is the IT company, a startup company they are doing in this area. Then we will go to the third week, which is a university panel, has a professor talk about academia research going on at different universities. So without further ado, I'd like to start today's agenda. So we lined up two distinguished keynote speakers for today, and also a distinguished panel and moderator later on. So our first keynote speaker is Dr. Dave Tennenhouse, who is the Chief Research Officer from VMware. And he leads the research and innovation activity that are accelerating and extending VMware's technology leadership. And Dave has a long track career and record of driving innovation in multiple domains. And in academia, and at his early career, he was a faculty member at MIT. And also in government, he was chief scientist of information technology service at APA. And in industry, he had several executive leadership positions at Intel, Amazon, and Microsoft. And in the last couple of days, we heard a lot of IT or technology terms like cloud computing, machine learning, and IoT, and etc. That's really his domain of expertise. And he's a member of Association Computing Machinery and a fellow IEEE and a member of FCC's Technology Advisory Board. So with that, I'd like to hand this to Dave Tennenhouse for his keynote speech. And for the audience, I apologize a little bit. We have a transition gap here, and going to upload Dave's slide deck here.
Actually, I don't have the slide just yet.
Okay.
Dave, I'm wondering, perhaps could we go to Arun, or while we try to get that set up?
Perfect. Great suggestion. So Dave, if you don't mind, we're going to move to the second keynote speaker. Then after Arun's talk, we're going to move back to your keynote speech, okay? So we have a backup plan. Our second keynote speaker is Dr. Arun Majumdar, who is scheduled to talk yesterday, but to acknowledge the shutdown state nationwide academia to recognize the anti-racism for the Black community. So he rescheduled to talk today. And Dr. Arun Majumdar is a J. Precourt professor at Stanford and a faculty member of the Department of Mechanical Engineering and Material Science Engineering. And he also has a long track distinguished career in academia, in government, and industry. So in government, he was a founding director for DOE APA, and also served as the acting Undersecretary of Energy from March 2011 to March 12. In industry, after leaving Department of Energy, he joined Google as a VP for Energy at Google. He's a member of National Academy of Science, member of National Academy of Engineering, and the AAAS. Now, he is also a member of board directors of EPRI. That's another connection in how we get together with EPRI to co-organize this workshop. So with that, I'd like to hand this to Arun.
Thank you, Liang. And I just want to acknowledge the partnership with EPRI, between Stanford and EPRI, and I really appreciate all the collaboration that is going on, and as well as with VMware and many of our ecosystem members. Now, I need some help. I have my slides ready, but I don't know how to upload them because that part is blanked out. So I may have the same issue.
You should see your slides on the screen right now.
Okay. Yeah, can you upload my slides and I can?
No, Arun, we already have your slide uploaded.
Okay, but I don't see that on the screen. I don't know what is being presented. On my screen, at least, there's only my picture and the bio. Did I?
There's probably a slight delay.
Okay. I still has not forwarded. Sorry, folks.
Aurelie, which slide are you seeing right now?
Right now, it's just the first slide.
Yeah, I think there's someone who said that's what we see too, which is, I think it's my picture and the bio, but not the full. Yeah. The first slide should say bits and watts, digital management of the electricity system.
That's correct.
But that's not what is coming, at least on my screen. Yeah, I think there's someone else who said viewers can only see his bio. So if there's a way I could upload, if I'm given the permission to upload my slides, I can put that up. But I don't have the permission right now.
Yeah. And this is David. Sorry to interrupt, but the link that you sent, I logged into Box, but it doesn't. It just says can't find the folder.
Okay, David, I'll work on that.
Okay, so what I'm going to try to do, if you give me one moment.
So Arun, on your left-hand side, you will see a small tab, has a number like 7 or 8.
Mm-hmm.
If you click, go to next page, then it will navigate. Yes, it is. It will navigate.
Ah, okay. Okay, thank you. Yeah, appreciate you telling me that. I learned something new. Okay, folks, so this is can everyone see the slide, bits and watts, digital management, electricity system? Yeah, I'm seeing some.
Yes.
Okay, thank you so
Yes,
much. Okay.
got it. Yes.
And my apologies for not being savvy on WebEx. Okay, so let me start by saying that there's a giant experiment that is going on around the world, and that is this lockdown of coronavirus. And the question is, what has it done to the energy system? I'm just going to give you one slide to make a point. And this is the work done by a bunch of students who are at home trying to gather data, and Professor Ram Rajagopal, who is also a member of Bits and Watts, on the change in demand of electricity and the change in transportation and mobility. And the different countries have responded differently. On the left-hand side, Italy and Netherlands, probably the most severe lockdown. And you have other countries, they're all in categories, UK, France, Spain, and then Germany, and California, and New York, etc. And what we're finding is that the mobility has gone down by 40 to 50%. And those who are in the oil and gas companies, the majors, have certainly reported that they've felt it. The electricity has gone down by 0 to 20%. And it really depends on the degree of lockdown, but not as much. So I think we're seeing that when the result of this giant experiment is the value of electricity that is around the world. And if you look at the profile of the demand around the world, what we are seeing is that the demand of the 20% reduction that we are seeing is roughly the same as what you would see on a weekend, the demand curve on a daily basis. So I just wanted to put this in front just to kind of highlight the importance of the electricity system. And as you will see, this is even more amplified by some of the other trends that we are seeing, which are the long-term trends. But this electricity ecosystem is going through a giant change, a tectonic shift as well. This is the curve for electricity generation. And when I was in the Department of Energy, we launched something called Sunshot in 2010, 10 years back. And just like President Kennedy had Moonshot, we said President Obama should have a Sunshot. And that is to reduce the cost of electricity production from solar to 5 cents a kilowatt hour by the end of the decade without any subsidies. And at that time, 2010, people thought this was a crazy idea. This was too difficult. And what has happened now, as you can see from the curve, is that now the power purchase agreements are signed at 2 to 2.5 cents a kilowatt hour. And what we are seeing that this has been the sunshot target has been achieved, just like the moonshot, before the end of the decade. And that's not the only thing. You'll see the wind, the blue circles also come down. And now what we are finding is that the cost of producing electricity is the cheapest for the carbon-free sources in many parts of the world. And that is the first time in history that carbon-free electricity at scale is the cheapest way to produce electricity. And this is indeed true when you see the dashed black line. That's the cost of electricity production from natural gas. And so today in the United States, while nuclear is one of the biggest carbon-free source, and so is hydro, we are seeing a shift going on towards renewable electricity. And as we see in worldwide, in the next 30 years or so, you will see a huge uptake not only in onshore wind, but also offshore wind, which is coming down in cost, as well as solar. Now, while this is indeed a very good news story, you have to realize that the grid, what I call the Tesla Edison architecture of the grid, was never designed for fluctuating generation. So that I just want to put that in the background, and we'll come to that. So if you look at the electricity changes, what we are seeing, I'm sorry, this animation is gone now. The black line of generation to transmission to substation to distribution and then to our homes, that was the original structure or the architecture. And of course, the transmission is a mesh network. The distribution network are sort of radial networks. But as we introduce more than 50% of solar and wind on the grid, what we're finding, and this is in California and many parts of the world, we see what is called the duck curve. That is, in the middle of the day, the net load that is remaining after solar and wind sort of goes down, and then it ramps up significantly. And that is on the generation side of the grid. On the demand side of the grid, we are also seeing some dramatic changes. One is electrification of transportation, which is, of course, as we now know, is network. The biggest loads in the home, now with LEDs being introduced, the biggest load is going to be heating and cooling. And now with network thermostat, that could be managed, that could be controlled as well remotely and aggregated. And of course, now rooftop solar is also growing, and that the inverters, et cetera, can be networked and controlled and monitored. So all these individual appliances, electricity appliances that are being introduced can all be networked, and these can be aggregated in the cloud, and thereby these could provide services not only for the wholesale market for addressing the fluctuation in generation, but also in the utility scale as well. Now, what you're really seeing is the development of an overlay architecture of information technology that will provide this balancing act, because otherwise your fluctuation both at the two ends of the grid, which could be disastrous if we don't manage it in an automated way. So this is the architecture that is changing and the overlay, and this is kind of the premise of our initiative called Bits and Watts, is that can we enable this to happen so that this coordination between the services that are provided for the utility scale doesn't mess up what is going on in the wholesale market and vice versa. So now I talked about the electrification. Let me tell you what's going on out here. The cost of batteries has come down, just like in solar and wind, has come down dramatically. And in the next few years, we expect the cost of batteries, the capex of batteries, to come down to about $100 a kilowatt hour. Why is this important? It is at $100 a kilowatt hour, the electric vehicle becomes range competitive and cost competitive with gasoline cars without any subsidies. So this is a big threshold. And as you see on the curve on the left, you'll find that the projection, at least, of the uptake of EV, new sales, is going to be around about 50% in the next 20 years or so. So this is a massive tectonic shift in the auto industry, which has relied on oil for the last 100 years. And so, as you can see, there's a massive change in supply chain. The transportation is to rely on petroleum supply chain, which it will still do, but there's a shift going on towards the electricity supply chain. So if you really look at what's going on, and this is something that a project that we started within Bits and Watts called EV50. How do we enable 50% adoption of electric vehicles, and what do we need to do to get there? But if you step back for a moment, there are three industries that are all growing that are being connected right now. So you have on one side the transportation industry, the automobile industry, which is roughly about $4 trillion per year, which is annual growing at about 3.3%. The electricity industry, which is roughly around $3 trillion and an annual growth of 2.5%. And the IT industry, which is at about roughly $5 trillion, growing at 3.7%. And right now, the electricity industry and the automobile industry never had to speak with each other. The regulatory, the incentives are totally different. And so there needs to be a common language between these two industries to enable this integration and transformation. And that language, we think, is going to come from the information side. So as part of this EV50, we are developing a cloud-based command and control software stack at different levels with the right APIs that we like to develop collaboratively with the industry to enable this to happen. And I think you're going to hear more about this later on. But this is a network overlay on top of the electricity so that the utility industry from one side and the automobile industry can actually talk to each other with the consumers and enable this thing to happen so that we manage the grid to provide the charging services at the most cost-effective way possible. And this is not just for transportation. At Stanford, we have something called, Stanford is a living laboratory. And what we are doing is to use our campus as an experiment in itself. You can see the picture down below of these three big tanks. The Stanford electricity system runs by drawing electricity from the grid and running a giant heat pump with cold water on one side. Those are the two gray tanks, and hot water, which is a red tank. It's not red hot, but it's just colored red. And we use these hot and cold water for heating and cooling, which is also electrified. And we think this is better. In fact, it is lower emissions than cogen plants. And it is really trying to future-proof our system because the electricity system will be the first one to be decarbonized. And of course, we have our transportation system, et cetera. But we're trying to use the integrated campus as an energy system in itself to try out our algorithms, to try out our architecture, and so that it is scalable and thereby take it out later on. And we have our labs of Bits and Watts labs, and we have batteries. And what is not shown out here is a thermal storage, a water storage as well, which is 1/10 of the cost of lithium-ion batteries, but extremely important for our energy system. And a few other examples. This is one of my pet projects of using machine learning to look at and develop an energy atlas for the United States. And this is using a satellite imagery and developing a deep learning algorithm, in this case called Deep Solar, to really become better and better with training to identify solar panels around the country in the contiguous states. And what we now have is the GPS location and size of every solar panel in the United States. And we're looking at the evolution of this going back in history of where the adoption has taken place. And we are now using Street View to figure out the grid as well, the distribution network. And we're slowly building up the energy atlas. And there's been a huge demand for this. And when we published our paper a couple of years ago, we have received requests from not just cities and towns, but various countries to see if they could do that. Because many a times, the recording of where these assets are not quite there. And of course, some of them are critical assets. So we have to be careful of how we present that to the public. So just to summarize what we're trying to do at Stanford in this Bits and Watts initiative, our mission is to enable the electricity ecosystem undergo the digital transformation. And this is not because the digital is available. This is to really cost effectively and urgently achieve its goals, which is decarbonization, energy efficiency, security, and the reliability. And that is why digital is important, to make this cost effective and to do it in a rapid fashion. And the mechanism we are using at any university is to use the research and education and to translate that into practice. We have decided that whatever we do in Bits and Watts will be open source hardware and software solution. We'll just make it available for people to use. And of course, our greatest asset and our product are our people. And the way we spend a lot of time trying to discuss what does our success look like. And we had debates and discussion. What was absolutely unanimous amongst our faculty and students was not how many papers and theses we produce. We know how to do that. But it is when our industry adopts and implements our solution, the solutions we develop, that is what we consider success. And the other part is the holistic and integrated education. This is not just a technical issue. There are regulatory changes we need to develop. There are business model innovations that we need to have, and there are financing challenges of standard assets, et cetera, that we need to implement out here. So this education of integrating technical, regulatory, business, and finance is something that we are trying to adopt out here, not just for our students, but from our industry and government. And at the end of the day, one of the impact is going to be how we impact policy, which is so critical in this electricity ecosystem. So let me stop here. Thank you very much for your attention.
Terrific. Thank you, Arun. Then we are still trying to get Dave's keynote slides. So I would propose a slightly agenda change. So Nicola, I'm going to introduce you and hand this to you, and we can start the panel conversation and make sure that you can end the panel discussion 15 minutes before the scheduled time, so we can have Dave to give the keynote in the end. How's that? Okay.
Yep, sounds great.
Let me see. So, Nicola Peill-Moelter, she is Director for Sustainable Innovation at VMware, and she helped put together this distinguished panel. So she has been in the sustainability innovation in the IT sector for a long time, and before VMware, she was the Senior Director of ECMA, and she's also a board member of a Renewables Buyers Alliance. So with that, I'd like to hand this over to Nicola and to introduce our panel speakers.
Great, thanks, Liang. Yeah, so I'm excited to moderate this awesome technology panel. They all represent companies and panelists that have significant and valuable experience in the fields of both energy and data technology. And they also represent companies, Microsoft, Google, and Intel, that have made major commitments to renewable energy and its seamless integration with the grid. So Google and Microsoft are the largest purchasers, corporate purchasers of renewable energy through power purchase agreements, virtual power purchase agreements, on-site and green power tariffs. And Intel has committed to develop the most efficient computers on Earth. So I think they're all highly well qualified to be on this panel. So let me introduce them briefly. We have O.P. Ravi, who's a principal program manager at Microsoft, and he's been in the IT industry for 22 years, mostly with Microsoft, and has worked on a variety of not so insignificant projects like Bing Search, Azure Cloud Computing, and Azure Big Data. He's currently leading the IoT for energy and is developing capabilities and product strategy for grid modernization, e-mobility, and sustainability. And he also recently released the Azure Time Series Insights, which is an analytics platform to analyze and visualize time series data for utility operators and other industry users, and has been working on the digital twin of energy grid and distribution resources. So he's got a lot of knowledge to share with us today. We also have Prithpal Khajuria. He's the global segment leader in the power sector and industry solutions division in the Internet of Things group at Intel. and he's driving IoT product and solutions for the utility industry. The vision of Energy IoT is to help OEMs develop solutions for utilities in managing traditional and next generation infrastructure in a seamless, secure way that's ready to deal with all kinds of cyber and physical threats. The scope of the Energy IoT solutions includes generation, transmission, distribution, and consumption of electricity. Then we also have, third but not least, is Raiford Smith from Google. So he leads the team with global responsibility for Google's data center, energy, and location strategy analytics, economics, and community development and energy teams. That's a mouthful. He has 29 years of experience with electric and gas utilities, including the Southern California company, Duke Energy, CPS Energy, Entergy, and holds various leadership roles in analytics planning, distribution, product development, and management, energy trading, legal and mergers and acquisitions, and technology. And he also holds 7 patents on grid optimization and electric grid technologies, and has published several papers on the future of electric grid, energy efficiency, assets optimization, and price forecasting. So that's very, very in line with what we're talking about today. And I also want to mention that Prithpal also has some experience working with utilities and service providers to help deploy connected devices and edge platforms in cloud architectures for operational excellence. So we have, I think we couldn't have had a better group of panelists today to speak. So with that, I want to let OP take it from here.
Thank you, Nicola, and I'm excited to be here. First of all, thank you everybody for joining this time. So I'm OP Ravi, as Nicola appreciated nicely or reworded nicely. Thanks again. Today I'm going to talk about what Microsoft and we are doing in this power and utility space. First, I'll start with the innovation in the technology companies happening, and Raiford and Prithpal can also agree or comment on that later. See, we were kind of most of the innovations are happening in the cloud at this moment, because cloud provides you the hyperscale and seamless connections and all those global presence, so you can do really a scalable solutions in a cloud. Then the next, sorry. Oh, there is a glitch. I have a few animation here, but I can talk through. So
unfortunately, I'm sorry, OP. Unfortunately, animation do not run it on WebEx.
Oh, no worries. So the next wave after cloud comes to IoT, where IoT allows you to connect your devices and assets to find the insights in real time and take some action for your business discussion. With IoT and cloud, we learned that, hey, especially in power and utility space, we need edge and AI computing also, because there's so many scenarios you need a hybrid solution along with the cloud. So that's why the third wave came with the edge and AI added the intelligence and all those things. So it's not only just a gateway or a device on an edge, but it's an intelligent edge where you can run the machine learning and AIs and all those things and leverage the cloud to train and take some decision on the edge. And the final innovation, or the where we are spending or investing a lot of things, is how we can leverage the digital twin concept in this new world. Because we need to look at the holistic picture and digital twin allow us to model not only the devices, but all the people, places, processes, and all those things. So that's kind of a wave like the cloud, IoT, edge, AI, and the digital twin. So as you can see, as Arun mentioned, that, hey, there is a lot of decentralization, decarbonization, and electrification happening. The price of batteries is reducing drastically compared to a decade ago, and so on. And these are the all important area. And as part of IoT is going to enable all of us to contribute and innovate in these three areas. And today I'm going to share maybe quickly, very briefly, 3 examples what recently we did in these 3 areas. So as you saw the countries chart, which Arun shared, how the trends are changing. Similarly, prior to the COVID, as you know, Norway is kind of committed for the electric vehicles, and they are leading the adoption. But in return, that's causing a lot of infrastructure overloading. So Norway in Agder Energy is one of the 3rd largest hydro generation company in Norway, and they also DSO, managing the distribution network and the operator roles. So the challenge for them was that, hey, their infrastructure is kind of getting really running hot to meet the new demands and capacity. And to upgrade those infrastructure is going to cost like millions of dollars and a lot of multiple years. So we partnered together and we innovated a smart grid solution, which uses basically the digital twin to kind of replicate their entire grid and network. Then we use the machine learning and AI to predict and having an accurate forecasting about when the load will be a problem or when they need more capacity. And then we use the kind of a virtual marketplace for the consumer and prosumers, and using the optimization to load balance the entire grid without, and that's helped them as well as to a consumer to kind of defer their costly investment, and consumers get a lot of benefits and transparency. The second example, I want to talk about the sustainability, and that's also very important. And if you know, I'm glad that every company is setting aggressive goals, and you might have heard the Microsoft commitment also, which will reduce our carbon, not only reduce and carbon neutral, but also kind of remove the carbon in whatever we have generated or contributed since our founding year. So with the Vattenfall, we worked on this 24/7 renewable energy project. Because the consumer as well as the generation companies are looking that, hey, how we can get the real-time insight to reduce and monitor those emissions and the generation and so on. So that's the interesting project, because the traditional or the current way are not sufficient to meet those aggressive goals. We need the real-time and hourly basis so that you can, as a generation company, you can plan better. As a consumer, you can change your behavior or influenced by the other incentive programs. That's another interesting and innovative solution which we released recently. And then the last and the final, as also Arun, I'm glad that we are all talking the same thing. And EV is another very, very innovative thing. It's not only driving innovation in the automotive or in utility, but it's too much in technology also. And there was a lot of people ask, hey, whether Tesla is a automotive company or is a technology company or is an energy company. So in EV, we are working on the platform, again, building the platform and capabilities to do the smart charging and other scenarios. With allego, we build this solution where you can charge intelligently based on the grid constraint that, hey, what is going on in the grid network, what's happening on the emission, and so on. So that way you can have a more power and more flexibility based on the grid constraint as well as your driver preferences and so on. So here I shared like 3 examples to showcase that how decentralization or distributed energy resources are important for load balancing. IoT real-time data is important to measure the insight on the sustainability and the renewables. And the third is about the EV, that, hey, how we need to leverage, because EV is a beautiful innovation. It's like a mobile distributed storage as well as the contribution. So with that, I will pause and look forward to other questions and hand it over back to Nicola.
Thanks, OP. That was really interesting. So next we have Prithpal, who will talk about the work he's doing at Intel and some of the other grid technologies.
Yeah, good morning, everybody. Nicola, you're going to put the slides up?
Yes, orally, we'll put it up. Should see it. It's a little bit of a delay, so just
That's okay.
you can.
Yeah, in the meantime, slides come. So I like to share a few thoughts in the meantime. Is that at Intel, we think like a two ways. One is called footprint, and other is the handprint. Footprint is where we're trying to reduce our impact on the environment. And the handprint is where we're working with other companies, organizations to help them achieve their goals. And one of the goals which we have set for us to help utilities and put them on the forefront of innovation. So help them to drive the innovation to build a grid which is can seamlessly integrate renewables. Yeah, that's what I'm going to talk about it.
So, Prithpal, your slide has already uploaded. If you can click the button which on the left-hand side of the screen, there's go to the next slide.
Yeah, I don't see that slide yet. I think there's some delay probably, so they're not updated on my side yet.
Actually, you need to click on this. There's a menu bar on the left. I can click for you if you want. Are you able to see Prithpal?
Yeah, OP, if you can do it, go ahead, do it.
Okay, I can see it now. Okay. I can see now slides. Can everybody see the slides?
Yes, we can see them.
Okay,
yeah,
so we'll talk about today is that bidirectional grid. You know, the grid is becoming bidirectional in front of our eyes. If we do something or we don't do, it's happening. All the rooftop solars, parking lot solars is all basically feeding power back to the grid, and which is driving the bidirectional grid. But as more and more grid integration is happening, what are the challenges we are facing into the grid? And one of the biggest issue we found out is that doing our research at Intel, that more and more renewables are coming, more and more instability in the grid is happening. How do you deal with going forward with solar, wind, storage, electric vehicles? Just a simple example, you know, one electric car is kind of simply equivalent to one house load, you know. If every house starts getting 2-3 cars, all of a sudden the load on the grid is basically going to quadruple, okay? A double, quadruple. How are you going to deal with that? So in order to deal with that, I think there are 4 pillars we need to look into it. First, how to modernize the automation and control in the grid. That's critical. The second thing is this distributed grid will require new set of security systems, and we need to build a flexible security system which can meet the needs of tomorrow, because today's best security system might not be the best tomorrow. How can we have a flexible system? And the next one is the deployment of applications in the utilities infrastructure. What is our process today? You need to put a new application, buy a new box, put on a truck, send a couple of folks to go deploy them in the substations. That's not scalable in future. And the last and more important thing is getting more insight into the grid. How do we make the grid more carbon aware? That means that as a renewable come back to the grid, how can we predict that and how can we deal with that? So I think this is kind of a slide which Dr. Rahul talked earlier, is that basically disruption is happening in the marketplace. The cost of renewable is going year by year down, and the penetrations of the DERs is increasing. But in our research we did in a couple of years back in Germany, we instrumented one substation and learned from it. Every X of renewables coming into the grid, it is creating 3x instabilities into the grid. The voltage is the first thing, the frequency, the power factor, stressing the infrastructure. all we see that happening. And currently, we are not building any technologies to deal with it. So I think we need to make the next grid to deal with all this stuff. And that's where we call it a software-defined systems to be deployed in the grid. And when we mean by software-defined system that all the substations in the utilities infrastructure need to be digitalized. They need to be virtualized, use the capabilities of analytics and AI, forecast feeder by feeder, because it is going to look like in future a grid of microgrids. And we can see each feeder will look like a microgrid. And how can we intelligently monitor that feeder and see what is happening at that feeder, how much renewable is coming, when it is coming, how to balance the feeder, in leverage all the resources available along the feeder. I think as one of the area which we thought about, experimented with it, was basically you might have deploy a strategic locations along the feeder, the storage. Renewables are already penetrating there. So storage will be a pretty in the homes, but along the feeder. If there is too much renewable coming back, which I have seen with multiple utilities, some of their feeders are getting overloaded because too much sun is shining, all the power is coming back to the grid. And we don't have an infrastructure right now to build. The only thing it is doing, stressing your infrastructure, increasing the technical losses, increasing instabilities, basically stressing the transformers. So there's a whole bunch of things start happening as the flow of energy starts coming back. So in future, we need to put basically is distributed storage along the feeders. If there's too much power coming back in, we can store into those batteries. And then when the shift that the clouds come in or our renewables go down, then immediately the feeder can handle itself and start discharging those batteries, stabilize it, and report to the control center that based on the weather trend, I have next 30 minutes, 1 hour of stability for the feeder, and then we will need excess power after that. So that's what basically intelligence need to happen at the edge, the feeder profiling, the load at substation level, and how all that information can be fed into overall planning of the grid. So one of the experiment Intel did here was that working with a couple of utilities, we basically build the infrastructure, put into their substation, and so preparing them for this journey, because utilities are also looking this way that, hey, yeah, this is happening. This snowball is getting bigger and bigger every day, and we need to build the infrastructure which can handle all these future applications. So in order to deal with that, the first step is to build the infrastructure. What we call it a micro data center at the substation, where we build this data center, aggregate all the data, and start running these algorithms and start balancing it. That is the future, what we need to modernize the grid, combine all the distributed resources, and make it a very seamless system going forward. Thank you very much. And now I think Raiford.
Yeah, that was great. Yeah, so we're going to have Raiford talk, and then we'll have some time for Q&A. So if you have questions for the panelists, please put them in the Q&A panel. Thanks. Raiford, take it away.
Great, thank you. Appreciate it. And good to see everyone this morning, and thank you for your time. I'm going to speak briefly about our transition at Google from moving our data centers from being 100% renewable energy to around-the-clock carbon-free energy. So first off, one of the things that always gets asked is, how much energy does Google use? Well, we use a lot, and we have multiple products with over 1 billion users. And all that technology really drives an enormous amount of computing capability. This is a picture of one of our data centers, and it's roughly the size of about 235 football fields. So data centers can be quite large, and they consume a lot of energy in doing all of the computing necessary to support those 1 billion users and computing capabilities. We have data centers all over the world, not just in the United States, but in Europe, in Latin America, and in Asia, and many more on the way. And to put our energy consumption really in perspective, we used about 1.5 times as much electricity as the entire country of Luxembourg in 2018. So that's quite a bit. But with all that consumption, though, we have to be mindful about how we use the energy. We are typically around 2 times more efficient than a traditional data center. Between 2010 and 2018, we've actually grown roughly globally 550% more computing is being done in data centers, but only about 6% additional energy has been consumed. And really that's been gained because we've been able to grow at hyperscale. Those massive data centers, get a lot of efficiency out of them, and it's a lot more compact than the traditional data centers that we are supplanting. With that, and apologies, there's an animation here that shows our growth in renewable energy purchases. But we've been buying renewable energy really since 2010, and they're projects that are really all over the world. At the same time, and once again, my apologies, there's an animation that shows here, but it would show that our total energy consumption relative to renewable energy, we've been able to chip away every year starting in 2010 to ultimately match and meet 100% of our electricity consumption with renewable every year, beginning in 2017, all the way up till today. With that, as was mentioned earlier, we are the largest buyer of corporate renewable energy worldwide, and we suspect that we will continue to be in that space for quite some time. And once again, another animation. These animations are really great, by the way. Apologies, I can't show them to you. But we also use our own technology to help drive efficiencies. As a matter of fact, we're using DeepMind to help schedule and dispatch wind resources for 36 hours ahead to improve not just wind power output, but how we perform in the market. But doing all of that is really just the beginning. And while we've been successful at getting to this point, we really think the future is around going towards 100% renewable, carbon-free energy for every Google facility in all places at all times. Before, we were matching it on an annualized basis, on a global basis, but trying to match every facility in all places at all times is a much, much harder problem. One of the things to show you that is this heat map that shows where green is the carbon-free energy supply that we have, and black represents the energy that is not carbon-free that we've actually been utilizing from the grid. And you can see that it's an imperfect match. There are a lot of gaps in here on an annualized basis at any given data center. Case in point, here's one from a snapshot in Chile. And what you can see is that, and this is solar energy that we have, in addition to a lot of wind and hydro that are already on the grid. The solar, as you can see, we produce way more in the daylight hours, but we have a gap in those other hours where we need to balance that out. And so one way to think about that is like, this is the status quo without our purchase power agreements in Chile. And you can see the black areas, no carbon-free energy, and the green areas are carbon-free energy. And you can see that we're not doing a very good job. There's roughly 56% carbon-free energy around the clock. If we add in our PPAs, you'll see that we actually jump and do a lot better. And this first solar PPA that we did improved it from the 60s to the 70s percentage-wise in terms of carbon-free energy. And we then continue to improve the data center's hourly footprint by how we improve our efficiency and use of that resource. And then ultimately, we add in a new PPA that fills in some of those gaps, the mixture of wind and battery storage, and that helps us get to about 97% carbon-free energy. Obviously, those last few percentage points are really difficult to get to, but you know that's the objective that we'd like to achieve. And so with that, that's a very quick overview of where we're going in terms of technology, efficiency, and our data center fleet to get to 24/7 carbon-free energy. I look forward to the questions and really have an opportunity to speak with folks about their questions about our journey. So thank you very much.
Wonderful. Thank you so much, Raiford. Yeah, so we already have some questions for the panelists, and I have a few of my own. So if we run out of those questions, I'll start my own. We have one came from Prithpal. Is there a view on the optimal amount of insight and vision in the grid? And if a utility has an opportunity to crawl, walk, then run, is there a view on what vision and digitalization efforts should take place first? So I think that's open to all panelists because you all have experience in this area.
Yeah, so thank you, Nicola. So I think in my view, the first step to start it from the utility perspective is the substations. They are the key to the delivering the power to the consumers, whether they are households, small businesses, or large businesses. And integration of the various resources need to start from there. And one of the, I think, what utilities have been using this ADMS for looking at their whole network. The ADMS needs to become a system of systems where a edge ADMS needs to run in the substations, and that is where it has to collect the data from all the sources along the feeders, come up with the algorithm right there, okay, how to balance and manage this particular feeder, then feeder by feeder, and then feed that information to the central system that, okay, what is happening and what is happening, what is currently out there. It is a one-way system, what is a model-based system where somebody puts a model together in the data center in their system one time, and there is no feedback to it. And what we need to build is the data-driven model where if we have a data from the edge and the model can be generated, and then the model inside the feeder inside the substation can sync with the model which is running in the distribution control center. I think that is the journey utilities have to go through, and which will be what I call it a utility 2.0, a utility with a bidirectional network, and it is composed of microgrids, a grid of microgrids.
Great, excellent. OP or Raiford, do you have any comments around that question?
Yeah, I mean, I agree with Prithpal. I just want to simplify his wording that, hey, I think all utilities are definitely adopting and working on this new technology. The need here is, in my opinion, working with many of utilities, we need to fast track the adoption of advanced and new technology. I know there is a lot of policies and regulation limitation, but we need to improve and come up some new ideas on that. So my crawl walk phases are going to connect 100% and collect all the data, because once, as Prithpal mentioned, the substation is very important. Yes, we need to look at the holistic picture and get both consumer, generation, transmission, and all those angles. So my crawl is that we connect as much as you can. Our goal is 100%. Then the second phase will be the collect all the data by connectivity. And then once you have all the data and the connectivity, then you can definitely optimize using this machine learning or AI optimization that, hey, which resource or distributed resource I need to participate or use in the market, or which substation is running hot and which substation can be used to optimize and so on. So basically collect, connect, and then optimize. Those are the three things I would suggest.
Thank you.
One quick thing here is that technology adoption without a business problem is called a science experiment. And that's what's driving all of this for all utilities and where they are in their various stages. There are really four distinct innovations or four distinct areas of change. The first is around data and analytics. It's being driven by customers, new technology, the digitization of the grid itself. That data is going to be used for new insights, but insights without other capabilities are kind of useless. And so One other area there's a lot of innovation that needs to happen and where utilities can advance the ball, all of us can, is around regulation and policy legislation to enable these things. Similarly, on the technology side, the physical hardware, the assets themselves, there's a lot of innovation going on in that space. And last and not least, our markets and the structured products that would be offered to do this. Each of these areas is experiencing a change. Utilities need to realize they can't run, crawl, walk, run in these areas without moving them simultaneously across all four fronts. And that's the strategy we're trying to use here, but certainly my advice to the utilities is also the same. Try and go move that slowly across all of those four areas.
Yeah, and if I could just make a shameless plug for the Renewable Energy Buyers Alliance, which brings together the ecosystem of renewable energy and integration to the grid on all four of those fronts. So if you have any interest, I would highly recommend you join the Renewable Energy Buyers Alliance. We're trying to address all of those points. Great. So we have another question. Prithpal, I think it's a little bit related to the last one, which is how feasible and scalable can we apply this software-defined network concept from substation automation to customer DER at home and the building level? And that's for all the panelists.
Yeah, so I think OP mentioned, connecting the things, it's very important to connect it. So if you look at what utilities have done, they are the biggest user of IoT. Take a look at the smart meters. All smart meters are connected in the country, I think close to 100 million or above. So we can collect the data from these smart meters and bring it to the substation. Technology is there, connectivity is there, it's feasible, everything is feasible there. Once we can bring the data from the meters to the substation, now all of a sudden it becomes a problem of analytics. Start applying the load desegregation algorithms, how in an anonymous way, without looking at it, how renewable is behaving, how storage is behaving, how electric cars are behaving. Once we got that information locked in, then all of a sudden we start looking at all the grid assets connected on those feeders to the substations. So start looking for that. We can pull all the data together. In REST technologies there, currently utilities can build what we call it a micro data center, buy the hardware, which is IEC 61850-3 or ANSI 1613 compliant servers, put those servers, put all the virtualization technologies, gather all the data. So everything is available there, and Intel has been working with some of our customers, and we experimented on some of these technologies, putting them together. So I think everything is there, as was mentioned, that the regulation or some kicker is required from the utility sides to start moving forward. And I think one of the kicker will come is as renewables are penetrating more and more, it's going to create more instability in the grid. And somewhere we say, okay, enough is enough, let's step up and now start doing it. And that's where the utilities are thinking about modernizing their infrastructure.
Excellent, thanks. Raiford or OP, any other comments on that question?
Yeah, the way we see penetration coming of renewables and intelligent assets, it's almost an inevitable outcome that utilities will have to shift from a centralized platform to a distributed one. There's just no way mathematically and physically you can pull all the data from all the resources, bring them back to a central point, make a decision, and send it back out into the field and have these assets operate in the time scale that's necessary. And additionally, it creates a giant security flaw, which is a single point of failure. And so shifting from a centralized platform to a distributed one, from computing, optimization, integration with third-party capabilities, is going to be a necessary step that utilities have to take. The technology itself, as mentioned earlier, IEC 61850, but also things like the open DSP or open field message bus, these sorts of capabilities at both the transmission level and the distribution level are necessary to really create that integrated grid.
Just to add one comment, I think the connectivity is there, and so if you look at so for example renewables, so one wind turbine can generate maybe 5,000 up to 5,000 signal per minute, and that is like more than a couple of GBs per day, and if I look at it in a month, like it's going to be in terabytes. So looking at scale of the data intelligently and having the models for those assets and how those models are connected to other things, because it's not only their device or one things to monitor, but having a context with around the entire grid. That's going to help us using this new digital twin or those kind of technology, that hey, how you can have the analytics which can give you the full picture end to end and then leverage those things. Yeah.
Great. All right, so an interesting one for Raiford, which is, do you see flexibility in demand profile of data centers being a service of which Google data centers will use in the future for aligning load with renewables? I think you're starting to work on some of that, but what is the reality of that?
Yeah, I mean, we had an announcement recently where we were doing some time shifting of loads. This is kind of the first key step in this space. At the same time of time shifting, there's also geospatial shifting, being able to shift it from one data center to another. I fully expect that as we go into the future, the ability to optimize and move things both temporally and physically is going to be critical. It helps us in resiliency, it helps in cost optimization, and most importantly, it also helps in carbon and water and general sustainability optimization. You get all these benefits at the same time by thinking through how best to utilize your load in a variety of resources. Similarly, I think efficiency will continue to play. AI and ML will continue to be big drivers in terms of how do we optimize asset utilization and how do we make things perform better with grid assets and third-party assets. So a lot of development to come in this space.
Yeah, I think demand shifting in general is a really huge area of opportunity, and I believe that some of the startup companies that we'll have on a panel July 8th will be talking about demand shifting platforms, which is super interesting. We have a general question for Arun, but I think the panelists can address this as well. As what kinds of business model issues and changes should we be anticipating and working on? I think maybe that's for the utility business models.
Yeah, this is Arun. I think I answered that in the chat box as well. So let me offer some thoughts on that. I think this was Terry Oliver from formerly at BPA who asked that. Well, just to give you a few examples, the utilities are sitting on a lot of data about the energy used in home, businesses, etc. They know which ones are inefficient, which ones are efficient. The demand curve can give significant insights about the inefficiencies, and there are, if you look at the demand curves, you can do, in fact, at Stanford, we did a simple machine learning to look at patterns. And it's actually quite staggering how unusual these patterns are of the demand curves of homes and businesses. So, utilities can think of using the data to provide services to to target the efficiency, because different kind of patterns will have different efficiency measures. So this is just a simple idea of using the data that they already have to create new services that can be done. I think as someone pointed out, electricity rates are really critical. I mean, for a long time, we had flat rates or tiered rates in California, which is ridiculous, frankly. Now we are seeing time of use rates, but time of use rate, why can't we have dynamic pricing? Because if you have dynamic pricing that reflects both carbon as well as the supply and demand inequities, that could go a long way in introducing innovations to reduce both your carbon emissions as well as your bills. And that will have new business models, et cetera, to use those rates in the right way. And one can go on and on. I mean, I mentioned about aggregating storage, aggregating loads or generation in the distributed level and providing the service in the wholesale market. That can be done today. But one has to be very careful in doing that, because if you, let's say, aggregate all the thermostats, let's say Honeywell decides to do that or Nest decides to do that. They don't do it now, but if they decide to do that and suddenly turn up the temperature thermal setting by 1 degree. And suddenly you get a huge drop in load. And while you can provide the service and make some money on the wholesale market, you could destabilize the distribution network. So some level of coordination, and this is where the regulatory framework has to be changed as well. Some level of DSO, distribution system operator, needs to be integrated into the system. Now, I'm just giving a few examples. There could be many, many more.
Yeah, just to add one comment, there's a new market for the consumers are also coming up, and there's an innovation happening in the nodes. So the nodes is a new marketplace for in the European country. That how the Nord Pool and other people are working to provide a flexible marketplace for the consumers, so that they can also participate. The demand response or the participation, or those are there in the industry for decades or more than that, but those are like not an automated system or not happening very intelligently. The utilities need to call the participant and get some insight and take some action. But those things will be going to change with this new technologies, that it's more automation, more intelligent decision can be taken, that which demand response or which participant can contribute in the grid. So having those insight and taking to the next level will be interesting to see.
Yeah, see, OP, I'd like just to add one thing. I think demand response was a good concept 20 years ago.
Yeah.
But I think the future of the grid is the flexibility. The renewables are getting at rooftops, and more going to be added. Cost of storage is coming down. And I think, how do we flexibly integrate and manage the grid in a way so that we don't have to have too many spinning reserves? Because right now, that's what the future is looking like. As more renewables we put in, more natural gas we are burning, okay, because to fill those gaps where things dip. And if we can basically build this technology and have the flexibility inside the grid as renewables going up and down, and it can adjust it, and we can reduce a lot of those spinning reserves which we have, and I think save a lot of money in that respect, and also bring the cost of energy down, because California has the highest cost of energy. We have highest penetration of the renewables, but we are not getting the benefit out of it. And I think that's what is needed right now.
Yeah,
to add the technology.
Yeah.
So unfortunately, this is an amazing discussion, and we still have quite a few questions. We're going to move on to David Tennenhouse, our second keynote speaker, but we will be capturing the questions and following up with everybody with the answers from the panelists in the near term. So thank you very much, panelists, and everybody give a virtual applause for a great job. Thank you.
Welcome.
Yeah.
Terrific. Thank you, Nicolas. Thank you for our distinguished panelists today. I think it's fascinating. A lot of conversation you guys maybe see from the chat. A lot of good questions. So I want to mention again, that's not the end of this conversation. That's a starting point from this conversation. And without further ado, I'd like to hand this to our another keynote speaker, Dave Tennenhouse. I think, Dave, you are in perfect position with your long-standing career in executive role on different IT companies like Intel. We have Intel represented here, and Microsoft and VMware, etc. So, already, can you help Dave to navigate the slides?
Yes, it's uploading right now. Just give it a few seconds.
Okay. Well, thank you very much. While we're jump in and let me know when it's uploaded. Is the audio good?
Yes, the audio is perfect.
Great. Okay, and we're ready to go. So thanks so much. And yeah, it's for me been just sort of great fun to hear about developments, particularly at Intel and Microsoft. These are things that I've kind of been involved in long ago when I was at those companies. It's really thrilling to hear what they're doing. And of course, always great to see the progress of Google. Been,
hey, David, a little muffled.
A little muffled.
Yeah.
I'll just try to speak up. Does that help?
Yeah, there you go. That's better. Yep.
Okay, thank you. Just jump in if I muffle again. So Google, has been just a great leader in the space, and also really appreciated the lead-off talk at Stanford. And I want to thank everybody, the organizers, for a truly professional job of adjusting the schedule when we didn't have the content all uploaded and ready. Everybody did a great job there. Thank you. So now I'm trying to get to the, I think I've got the advanced chart. So I think I'm clicking on the next there. Okay, great. So, I think all of us pretty much have been talking in many ways. If you look at these companies, we're all kind of involved, not just in digital grid activities, but really, tech is a force for good. It's a big thing for us at VMware. We're a younger company, so we're sort of newer to coming to the sustainability agenda, but we've come very strongly over the past couple of years. Like the sustainability team punching way above its weight with Nicola and others. So we quickly achieved carbon neutrality. And along the way, sort of just as kind of an example of one of the things that I found really interesting is when I visited our India team and found that they'd managed to achieve this. And energy in India is a difficult issue, often involving local generators and all sorts of things. And what I found was a really interesting new business model when I started poking around and asking questions is when we rented the office space, we actually got the power as part of the deal. So in other words, the landlord was basically much like McDonald's would say, do you want fries with those burgers? The landlord was basically saying, do you want clean energy with those guests? So I just wanted to mention that because not only is the grid changing, but the whole supply chain and how energy may be bought and sold is also changing in interesting ways. So to me, that was just sort of an interesting innovation. One of the activities we also would like to sort of invite people to participate in is we're setting up a microgrid on our own campus, which is in the Stanford Research Park. This contains some of the technologies other speakers have talked about before, batteries, et cetera. So we can have storage, but I won't go into that. But here's the real issue is the Stanford Research Park is much bigger, and then we've got all these great activities going on at Stanford itself. And wouldn't it be great if we could somehow build this out to be a much bigger microgrid, maybe think of it as a milligrid that actually kind of covers the whole Stanford Research Park and Stanford campus. So I just wanted to throw that out there as something we could work on for future innovation in the digital grid space. Something I think that hasn't been touched on, and I just do want to remind people is, although the IT industry consumes a lot of energy, I'm going to speak about that in a moment. In a lot of cases, people use the information technology to increase their efficiency. Right? That's we particularly work in the enterprise space, so enterprise users. If you really look at what they're doing with that compute, storage, networking, a lot of what they're doing is increasing the efficiency of their, using the virtual world processes to increase the efficiency in the physical world. So although we consume energy as an industry, in a lot of cases, we're net helping people save in a really, really big way. Now, having said that, we still are concerned about our consumption as an industry. This is kind of one of many charts. The green sort of here represents kind of the worst case, but also in some ways the case people thought we might have been headed towards a number of years ago. And we've really brought that down as an industry to somewhere between the red and the blue. And the Google and Microsoft folks have really kind of led the charge in a lot of this in multiple different ways, getting the PUEs down, et cetera. So I'm not going to go into that. Intel and others in terms of getting the server physical costs down. Well, one of the really big contributions here is actually in virtualization. It's basically requiring just a fraction of the number of servers than we would have otherwise been on course to have deployed. And just to sort of give people here a brief tutorial, I'm sorry about this, this is a brief advertisement for virtualization. When you typically have a server, you put an operating system on it, you put an application on it. That was the old way of doing things. But it turned out that most of those servers, the applications was only consuming a tiny fraction of the server. So most of the time, that server was idle. And simply put, what we do with virtualization, and I'm just trying to get the slide to advance. Sorry, folks. Is put a layer, a virtualization layer on the server between the server and the operating system, sometimes called a hypervisor. And now you can actually have many virtual machines, many virtual servers running on the one physical server. So you can now consolidate a large number of what used to be physical servers into these virtual machines running on a single server. And if you start playing that out at large scale across the whole data center, lots of great things happen. Interestingly enough, and I think it was the Google speaker that mentioned this, you also then have the opportunity to move these virtual machines around between servers. So you can actually move them around to more efficient servers within your data center, or better yet, move them across the network to other data centers where perhaps you have cleaner energy. And do this sort of time shifting of workloads that we've been referred to. So that's kind of a lot of the magic that VMware has been involved in since its foundation. Here's just kind of an estimate that a third party put together of just how much the world has saved by not having to buy and deploy in data centers all of the servers that we otherwise would have deployed without virtualization. So it's quite a kind of a big contribution that we're very proud of. And something I think we heard virtualization talked about by the earlier speakers. So I will say VMware has expanded its ambitions. We go far beyond just virtualizing servers now. We virtualize the network. We virtualize the storage. We also work at the edge. We work on the end user devices. With COVID, we've been very active because we virtualize desktops, and that's been helping people work from home. So just want you to sort of have a broad view of the things we do. But now, getting back to the question of reducing, the curve, this is a different flattening of a curve, which is the demand within data centers. We looked at, and Nicholas been actually particularly active in looking at what else can we do to flatten the curve. And one of the things is it just turns out that often in the data center, a lot of those servers aren't being used, and a lot of virtual machines are just sitting there idle, and people haven't gotten around to turning them off. The Stanford emphasis team actually studied this and found that the so-called zombies actually are a fairly decent fraction of what's going on in the data center. And people often, ask, so like, why do these things accumulate? And Nicola came up with this great explanation that it's sort of like, all those apps that somehow accumulate on your phone and you just never get around to deleting them. But by the way, they're still getting updated in the background and, sucking down battery power and network time and everything else on your phone and slowing your phone down. So wouldn't it be great to get rid of them? So, we did indeed do some looking around our own data centers, and we take advantage of many opportunities that when we're migrating a data center from one place to another, or we're consolidating multiple data centers together. The point of this slide is simply to say, yep, it's not just a Stanford study. When we looked internally ourselves, we found that we had lots of opportunities to get a significant reduction. And more interestingly, you might think, well, you do this once. But actually, it's a rinse and repeat because somehow, these zombies kind of keep appearing in the sense that things keep getting older, and people keep finding that they kind of, as they migrate to new systems, they're afraid to turn off the old ones. So we think you need, we're going to be ourselves and encouraging our customers to get systematic about this, so that they actually have a sort of ongoing zombie prevention cycle. So those are just examples of things that we've been actively doing in terms of sustainability overall. I know we're here today to really talk about the digital grid, and the goal for this workshop has been about defining these interchange requirements, et cetera. We just heard from the earlier speakers about many of the good opportunities to kind of basically re-engineer the grid to be able to take advantage of distributed power generation and sourcing. I'm not going to speak too much about that. A few years ago, I'd say, well, coming to this group, EPRI and Stanford, group, would be like bringing coal to Newcastle would be the English way of saying it. I guess now we might say it'd be like bringing solar panels to Silicon Valley. But what I do want to do is say, as much as we want to sort of create this software-defined grid, and we definitely at VMware want to be front and center on that, we also want to make sure people are kind of wary of unintended consequences. And it looks like bills don't quite work here, I guess, on this particular tool we're using for presentations. But, the bottom line is, many of us set out to build the internet and, kind of do great things, change the world. But we, ended up with a lot of unintended effects relative to, connecting everybody, for giving everybody a voice related to blockchain and the things that we set out to do. So we did a lot of good, but we also had some negative unintended consequences. So the message I want to talk about in the rest of this presentation is just that if we want engineering for good, if we want to build a great new digital grid, it's going to need good engineering. And that may go without saying to many people, but I want to put forward, and interestingly, each of these issues already came up with the earlier speakers, right? We're going to need intrinsic security. We're going to need a better approach to privacy. And I see this in some of the questions on the chat. I think we're going to have ways that all the different players, the different companies that are involved in that grid, it's going to be a whole bunch of new players. How are they going to trust each other in a decentralized way? So we approach it to trust. And we've got to make sure that this whole thing is super efficient. We've heard a lot about how machine learning will be used in distributed models to improve the efficiency of the system in many places. But we need to do that in ways that are going to create a robust overall effect. So I'm just going to kind of go through those topics really briefly here. Security, bottom line is, I guess what I'm going to say is, we the software industry, and I'm not talking about VMware or any of the one company represented here, but as a collective kind of, not just the software industry, but developer community, we have just got to do better, right? And security is one great example. For a large customer today, say a really large bank, they need to acquire and integrate sort of on the order of 100 different security products in order to feel like they're keeping up with best practice. And even then, they don't know if they've got security, right? So this is, kind of just really broken approach. And if you think about it, part of what's going on here is we have sort of, and it goes all the way back actually to the research community, we have people that instead of thinking about how to systematically improve security, they're finding exploits, and it's almost become a business model. Find an exploit, find a patch for the exploit, start a company and get VC investment, and then sell the company, and then rinse and repeat, do that some more. So we need to really get away from that model to much more systematically incorporating security into how we define and build products. I'm just going to sort of skip over this for a moment and say VMware has actually been investing in all the way back up to the research pipeline and improving the research pipeline and the joint effort with NSF to getting people systematically thinking about security. And we think software-defined infrastructure and virtualization is actually a great starting point for rethinking security. By the way, we have a similar program with NSF on edge-centric data infrastructure. One of the earlier speakers talked about needing to be able to get all that data from the edge and being able to operate in a decentralized way. So that program is also working on that. So lots to do there in security. We are very committed as a company, CEO down, to what we call intrinsic security and changing that landscape. Privacy. Here, again, I'm going to sound a note of caution. I think collectively we need, as a developer community, to have a stronger and better grounded view of this. One area I want to say is, I think, sort of bright ray of hope, but it only solves a part of the privacy problem. That this is the work on differential privacy that's been done by Cynthia Dorff. She started this work at Microsoft, now at Harvard. Really sort of great work. I won't go through the details so much as say that it sort of helps very much in the situation where you aggregate information from multiple parties. Can you make sure that that when people ask questions to that aggregated database, they can't reverse engineer the answers of any one individual? And I think this is going to be very important for some of those if we're going to sort of, kind of pull that demand information all together, probably as an industry, we could operate on the aggregates. We don't necessarily need to know all the individual information. So how can we get ourselves to be taking advantage of this differential privacy approach that gives you sort of some strong assurances, in effect, of how much privacy an individual is giving up by being part of the aggregate. It's a statistically based approach. There was a video here that's probably not going to play, so I'm going to skip over that, say there's an equation here, and the importance isn't that you understand this equation, but that actually what Cynthia and her colleagues have done is actually put privacy on a mathematical footing. That's why I'm excited about that, right? So we can actually start reasoning about privacy. Blockchain is an area, again, where things haven't turned out exactly the way I think the idealists amongst us would hope. You have this system that generates, it consumes in terms of the Bitcoin blockchain enormous amounts of power. You've all read about that. It's primarily a usage model, which, to be honest, by criminals trying to exchange money for their activities. And the worst part about the Bitcoin blockchain is it doesn't even achieve the one thing it was supposed to do, is give us decentralized operations. But when you actually look, you find that a small number of players actually control most of it. So having said that, those are problems with the Bitcoin blockchain. But when we looked at this a few years ago with our research, we said, hold on, don't throw the baby out with the Bitcoin bathwater. This idea of federated ledgers, the notion that you can essentially have a shared database that's shared amongst different organizations that have a limited degree of trust amongst each other, but don't necessarily trust every employee of every other company. So that the organizations want to work together, but would like to combine their information in safe ways. That seems like a very powerful and useful idea that could dramatically, reshape trust across company boundaries. By the way, amongst enterprises, amongst governments, we heard people talk about regulators in some of the chat and some of the questions. Interestingly, in a blockchain environment with these distributed ledgers, the regulators could actually peer into the ledgers and also be able to sort of reshape. You can actually change how regulation and audit work, I think, with this technology. So our view is that there's an opportunity to create grid blockchain. We've really been working, on this from this enterprise perspective, and that it's really about a new decentralized trust approach to how organizations effectively work together and share data. I'm not going to go into the details, but what I want to get across here is we looked at the properties that enterprises need and said, gee, you don't really need that proof of work to be able to pull that off. There's alternative consensus models that could be used. We engineered and came up with a system that Project Concord, which does not waste all that energy. It's very energy efficient, and also is got much better throughput and much lower latency. So you get much better performance, low energy, et cetera, from our scalable consensus engine. And Concord is an open source project. So finally, I want to go to this sort of question about being robust and efficient. And a lot of people sort of indicated we're going to get a lot of that efficiency by, I think that, we use machine learning to harvest, micro efficiencies. It basically will find us good optimization points for a given process by, studying the data. I think that, though, we are also, in order to make these things robust, going to have to leverage constraints, both to make sure that the machine learning is robust, but also to make the systems as a whole robust. So just some quick comments there. I think you probably all know that ML is eating the world. But, the issue here is that the part of machine learning that all the excitement's about and that is, allowing us to really solve learning problems that we just couldn't solve, or skills we couldn't solve before, these deep neural networks. And the issue here is, that it's really too good to be true. And when something's too good to be true, it probably isn't completely true. And for enterprises, when you start using machine learning for things other than cat photos, you have a number of issues in terms of the potential for either the data that's been used to train the system to be biased, or the model itself to become biased. Now, in addition, part of the reason for this is that we don't really deeply understand how these neural nets work. And if you don't understand how something's going to work, somebody else is going to figure out a way to attack it. because if you don't really have a great almost model of these models. So, you know, this is one example here. Again, it probably doesn't work well without the animations, but the bottom line is if you take a picture of a dog and you throw a little bit of noise on it, that picture, the human being will still see a dog, but the computer will see an ostrich. And similarly, if you take a stop sign and put a few stickers on it, as you can see with the stop sign, the human being will still recognize it as the stop sign. The computer will see, you know, 45-mile-an-hour speed limit sign. So this is now serious. This is not just about changing the picture dog for the dog to an ostrich. This is really putting people at danger. So, you know, we have a conundrum because we've got these systems that perform wonderfully, but we don't fully understand them. So we need to do two things. We need to learn how they work. That's the great research on explainability, and we're active in that as are others. But we also, as kind of, do have a moral responsibility. You know, if the machine learning system that we don't completely understand reads the X-rays better than the doctor, shouldn't we use it and let humans get the benefit? And the answer is yes. However, we need to constrain it and make sure we only use it in cases where we can get predictable outcomes. And we can do that potentially. Professor Khajuria at Stanford has suggested using statistical methods to essentially create a wrapper around the machine learning so that you can basically provide assurances that if you provide inputs in a certain statistical range, your outputs will be in a certain statistical range. At VMware, Nina, one of our researchers, has done some work that is similar wrapper activity, but using logic and constraints to essentially constrain the machine learning. She can do this for all types of deep neural networks. They can do it for a subtype right now called binary neural network. And that's kind of the proof of concept. Hopefully we'll expand that to other things over time. And the main message here is you can basically then provide assurances that if the inputs, for example, only change a little bit, the outputs will only change a proportionate amount. So you won't get these, like, you know, small changes in input creates a completely unexpected output. We're now taking that and applying it to something called deep reinforcement learning controllers. The key thing about these controllers is you can think of it, you know, if you see the line at the bottom from the environment, it's going all the way back to the beginning, which is looking at the left-hand side. Again, I'm sorry that the build doesn't work here. Then that's a classical feedback loop, right? And you can see the controller box in the middle. The interesting thing is this diagram has two feedback loops. You've got the rewards loop at the top, which says that we're actually also dynamically changing the controller. So in addition to having a feedback loop of the usual sort, the actual control logic itself is changing dynamically in response to what it's seeing. And we call this is called reinforcement learning. The reward is kind of reinforcing the controller, nudging it into better and better optimization. So this is really cool. This stuff gets used. Now you're talking about really real-time stuff, right? That we would put out at the edge, as Intel described, and it's sort of deeply, you know, in the grid and controlling and changing things in real time. And my point here is, so it's really important to be able to constrain this stuff. If we just pop into that controller a neural network that's unpredictable, we're doing the world a significant disservice. So, you know, we're very excited about the progress that's being made at this activity. We're going to use it in some of our own products, we hope, you know, kind of working with our product teams. But we think, you know, for things like this, it's going to be more important to our customers, so it's digital grid, other utilities, anybody running real-time processes. Now, in terms of other aspects of robustness, I think there's even a higher level at which we can work to make sure that these highly decentralized systems are reliable. And again, I'm sorry, this diagram is sort of a bundle because normally I would build it in an animation. But the important thing is if you see the two database-like things on the left, there's a current state and a desired state.
State, I am a reminder of the time.
Yeah, sorry, this is, I think, almost the last slide. Sorry. So I'll just get through this and stop. I apologize. I had to go. Usually I just go boom, 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 and I have to slow down because the build here. This is something that in the distributed systems world we've moved to, or we are in the process of moving to, that I'm really excited about, which is essentially you have a system, it's in a current state, you have a desired state you'd like it to be in, and you can essentially have an automated planner that's going to plan the steps to nudge the system into the desired state and be in real time monitoring how you're closing in on getting to the desired state. So that's one aspect, apart from the blue here with the blue and the red. What's important there is you have to do something like this in these highly decentralized systems, because given that they're they're distributed geographically, you have speed of light delays, right? So you can't just instantly convert the system from the current state to the desired state. By the time you move it partway to the desired state, things have changed, and your desired state might have changed again. The other part here is the part on the yellow, or gold, which shows that we have human beings, instead of being deep in the control loop, they're elevated to be on the control loop, above the loop, and they're basically setting the policies that are governing the new desired state. So this is being basically policy driven. So I'm just sort of excited about being able to take that sort of technology and use it to make sure that we have a very robust digital grid. So with that, sorry for the time overrun, but the big message here is we all want to do engineering for good. Let's make sure we put good engineering into this new digital grid.
Thank you, David. Really appreciate. And with that, I would like to say, this is not the end of this webinar series and not the end of this conversation. It's the starting point. We still have the summer starting from July 1st, and we lined up several panels to continue the conversation along how we can standardize a data platform, be able to engage customers. I already copy and paste the schedule in the chat. So for the attendees, please follow us, or you will receive the invitation shortly from EPRI regarding this summer webinars. So with that, I'd like to hand this over to Omar, and which is a co-organizer from EPRI. Omar, would you like to say a few words, and we can adjourn today's webinar?
I'd just like to thank everyone, all of the attendees and the panelists and keynote speakers for today. I'd like to give actually Mark McGranigan, our VP of Innovation, the last word. Mark, if you'd like to say any final word before we close out.
No, just thank everyone. I'm really looking forward to the whole webinar series, and I think this was a really good foundation for that. So thanks to all the panelists on all 3 days. It was a really great discussion.
Okay. Thank you, everyone. Thank you.
Yeah. Bye-bye.
Thank you, Leanne.
Bye. Thank you.
Thank you. Bye-bye.